This video is brought to you by ThePuzzlr.com. In this video, we take a look at problems 1 to 5 from the 2019 AIME number 1. Without further ado, let's now move on to the problems and their complete solutions. Starting with 2019 AIME 1, problem number 1. Consider the integer n equals 9 plus 99 plus 999 plus 9,999 and so on, where we finally end up with 321 nines in the same number. Find the sum of the digits of n. Okay, so there are a few ways to try and solve this problem, but you might probably want to start out by trying to find a pattern. We won't be doing that here. Instead, we'll be looking at a much smarter way to try and solve this problem. Trying to find the pattern would eventually work in this case, and you would get a valid answer. How can we continue here though? Notice that each number is 1 less than a power of 10. So if we had 1, so first of all, notice there's 321 numbers because there's one, this is one number, the second number, third number, and you notice the pattern. The number of nines in the number tell us what number it is. So finally, this would be the 321st number. So there are 321 numbers. Okay, so now if you add 1 to each of the numbers, we'll get 10 plus 100 plus 1,000 plus 10,000 and so on. We can rewrite this algebraically as n plus 321 is equal to 10 plus 1,000 plus 100. So we can write it as 10 squared plus 10 to the power 1 plus 10 to the power of 3 and so on. And finally, right here, we would have 10. We would have 1 followed by 321 zeros, which would be 10 to the power of 321. Now, adding up 10 plus 100, you'll just notice the pattern immediately. It would be 100 plus 10, which would give us 110. Adding in 1,000, since there's no carries, it's just going to be 1110. Eventually, it's all just going to end in 0. So, I'll erase this. We have 1 0 here, and now we can see the pattern. The pattern's pretty clear. What we can do is adding up all the numbers on the right would be 1, 1, 1, so on, and there would be 321 ones. So there's 321 ones, and then it would finally end in 0. Now let's subtract 321 from both sides. So we would have some number of ones here, let's say 318 ones, and then we would have a 1, 1, 1, and 0 here. And we could subtract 321 from this number. We would get getting 1 from the tens digit, 10 minus 1, 9, 11 minus 2 minus 1, which gives us 8, 11 minus 3 minus 1, which gives us 7, 1 minus 1, which gives us 0. And then we would have our 318 ones here. So that would be 1, 1, 1, 318 times. So the sum of those 318 ones is 318 times 1, or 318. In that, we add 7 plus 8 plus 9, which would be 15 plus 9, which is 24. So we would be adding 318 plus 24. Doing that, we would get 2 here, 1 here, 4 here, and this. Thus, our answer is 342. Let's move on to problem number 2. Problem number 2. Jen randomly chooses a number j from 1, 2, 3, all the way to 20. Bella then randomly chooses a number from the same set, 1, 2, 3, all the way to 20, but it's distinct from j. So we'll underline that because that's probably going to turn out to be important. The value of b minus j is at least 2 with the probability that can be expressed in the form m over n, where m and n are relatively prime positive integers. Find m plus n. Okay, so how many possible outcomes do we have? That's the first part of figuring out a probability problem, because it's the number of successful outcomes over the number of total outcomes. Well, the total number of outcomes, let's see, Jen has 20 numbers to pick here. So 20. And Bella, she doesn't have 20 choices because it has to be distinct. So we can see that already comes into play. So she only has 19 choices because she can pick any of the 20 numbers except for the one number that Jen just picked. So there's 20 times 19 choices. Okay, how many actually work? So we need b minus j to be at least 2. This seems like an easy casework problem. What we can assume, let's say b picked 20. Well then j can pick anything from, so if b picked 20, j can pick anything from 1. 1 obviously works. 1, 2. If it's 19, then it would be 20 minus 19, which would give us 1. So that's 2 less. What about 1 to 18? 1 to 18, 20 minus 18 would give us 2, which just works. Similarly, if we have 19 here, it would just keep on scooting down 1. So we would have 1 to 17 here. So when b is 20, 18 numbers work for j. When b is 19, 17 numbers work. And so on. We can keep on doing that. And eventually we'll end up with 0 numbers that work. So this is just the sum of the first 18 natural numbers. To calculate that, we use the formula n times n plus 1 over 2, which is the formula for the sum of the first n natural numbers. So applying it here, we would get 18 times 19 over 2. So you don't actually need to compute that. Let's just write it here. 18 times 19 over 2. That's how many numbers actually work. That's how many pairs of numbers that work. So the 19 cancels out. The 18 becomes 9 and this cancels out. So we're left with 9 over 20. This gives us 20 plus 9 as our answer, which is 29. Moving on to problem number 3. In PQR, PR equals 15, QR equals 20, and PQ equals 25. Points A and B lie on PQ. Points C and D lie on QR, and points E and F lie on PR. With PA equals QB equals QC equals RD equals RE equals PF equals 5. Find the area of hexagon ABCDEF. So I already went ahead and drew a rough sketch, but you could do this too. Now you might be wondering, mine looks like a right triangle, and how did I figure that out, or did I just assume that? Well, notice that the sides are 15, 20, and 25. You might recognize that as a Pythagorean triple, or it's a multiple of the Pythagorean triple 3, 4, and 5. We can quickly double check that. 15 squared, which gives us 225, plus 20 squared equals 25 squared. And double checking, 225 plus 400 equals 625. This is obviously true, so this is a right triangle. Okay. Now let's label our points. So they tell us, scooch down a bit. So they tell us that the right angle would be this angle that's right here, so that would be R. That's the angle that's both in PR and QR since they're the legs. And we can make, let's make this one Q since QR is longer than PR. So we have this right here. Let's just erase that to make it a bit neater. We have PRQ. They tell us PA, so points A and B lie on PQ, C and D, and finally E and F would be just right here. Okay, so they tell us PA equals PE, BQ equals, so we have PA equals BQ equals QC equals DR or RD equals RE equals PF, and they're all equal to 5. Okay, find the area of hexagon ABCDE. So now this hexagon is super weird looking, and you could go ahead and find a way to find the area of that hexagon, but instead we're going to do something else. We're going to find the area of this triangle, this big triangle PQR, right here. So this is the big triangle PQR. And once we've found the area of big triangle PQR, so let's undo that. Once we've found the area of big triangle PQR, we're going to subtract triangles PAF, EDR, and BQC. And we'll be left with our hexagon, which we have to find the area of. In a way, it's similar to complementary counting. Okay, So now you might be wondering, how do we find the area of these triangles? Well, easy. What we can do is, there are a few formulas that you can use to find the area of a triangle. You can use the normal base times height divided by 2. Or you can use Heron's formula. We won't need that over here, but you could use that. Or you could use the sine formula, which states that 1/2 times AB times sine of angle C. So that would be two sides and their included angle times 1/2. That also gives us the area of a triangle. There's also other formulas including some radiuses, but we won't need that for this example, for this problem. Now, what's the area of triangle PQR? Well, we know that PR, so that would be PR, since it's a right angle, PR times RQ divided by 2. We already know PR and RQ, that's just 20 times 15 divided by 2, or 150. So we'll erase this to make more space, and we'll write it here. So triangle PQR that symbol represents area is equal to 150. Now we know that this is 5 and this is 5. Although we don't necessarily know this angle, we just need the sine of that angle. And remember, the sine in a right triangle is opposite over the hypotenuse. We can use that information here because we already have the length of the opposite side and the length of the hypotenuse side. Let's find the area of triangle APF first. So the area of triangle APF is equal to, so one of the things that it's equal to is sine. So first we have our 1/2. So 1/2 times sine of angle APF times AP times PF. They tell us that AP and PF are equal to 5. So we're multiplying by 5 times 5. Now sine of APF is, so this right here is opposite, which is QR, over the hypotenuse, which is PQ. QR over PQ. Now, going back to the original problem to see the length of QR, we see that QR is 20 and PR is 15. So let me move a bit here. QR is 20 and PR is 15. So this right here, QR is 20 and PQ, the hypotenuse, is 25. So this is 20 over 25. So this is equal to 1/2 times 20 over 25 times 5 times 5. This cancels with the 25. 20 cancels out with the 2, leaving us at 10 in the numerator. So the area of triangle APF is equal to 10. Let's move on. Area of triangle EDR. So EDR, you could use this sine formula, but that's just a normal right triangle. So that would be 5, the legs times itself. So 5 times 5 divided by 2. So triangle EDR is equal to 25 over 2. Okay, what do we have next? Triangle QBC. Triangle QBC. Well, that's equal to BQ times QC. 1/2 in the beginning. Never forget the 1/2. That's a very silly mistake that you can make and get this problem wrong. And then the sine of the included angle. So that would be sine of angle Q. But instead of writing out sine of angle Q, we know that PR is equal to 15. And the hypotenuse PQ is equal to 25. So we can directly write 15 over 25 as a sine of angle Q. Now BQ and QC are both 5 because the problem tells us that in this long equation. So we have 1/2 times 5 times 5 times 15 over 25. Here, the 5s cancel out with the 25, and we're left with 15 over 2. So the area of triangle QBC equals 15 over 2. So we have to do the sum of these three triangles. So we have this, converting it to a common denominator, 20 over 2. We have 20 over 2 plus 25 over 2 plus 15 over 2, which is 20 times 3 over 2, or 60 over 2, which gives us 30. So 60 over 2 gives us 30. So you might recognize that the number 20, 25, and 15 were actually the side lengths of this triangle. And yes, you could have used something along the lines of similar triangles to solve this problem. But I think this way was probably the easiest to spot and calculate. So we have 30 as our sum of these three triangles. And you would be very wrong to write your answer as 30. Because now we actually have to subtract this from the total triangle, 150 minus 30, to actually get the area of the hexagon, which would then be 120, which makes sense. This triangle approximately looks like half to 4/5 of the whole triangle. This hexagon looks like half to 4/5 of the whole triangle, and the whole triangle we already calculated was 150. So our answer is 120. Moving on to problem number 4. Problem number 4. A soccer team had 22 available players. A fixed set of 11 players starts the game, while the other 11 are available as substitutes. During the game, the coach may take as many as 3 substitutions, where any one of the 11 players in the game is replaced by one of the substitutes. But if you've been booted from the game, you cannot re-enter the game, although a substitute entering the game may be replaced later. And you're not doing any substitutions at the same time, so they happen one by one. The players involved and the order of the substitutions does matter. So let n be the number of ways that the coach can make substitutions during the game. This includes the possibility of making no substitutions. Find the remainder when n is divided by 1000. Okay, if you're solving this problem, first thing that you'll notice, we have 11 players that are already fixed. You have 11 players, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 players that are already fixed. And then we have 11 players that we already subbed out. That start out the games being subbed out. And this set is fixed, so we're not choosing this set initially. This is already fixed. So we can say that this is player 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And maybe I'll call these players by their letters. A, B, C, D, E, F, G. I don't think I'll need this information, but it's always a good idea to write it down. A, B, C, D, E, F, G, H, I, J, and G. Oops. And K. Okay. So for the first substitution, we have 11 choices. So let's look at this based on casework. We can do 0 substitutions, which is already one way. We can do 1 substitution, 2 substitutions, and 3 substitutions. Okay, so for the first substitution, we just have to pick one of the 11 players that we want to substitute and one of the 11 substituted players to substitute back in. So that's just 11 times 11. Now we build on this for our second substitution. So for our second substitution, so we already have 11 times 11, but let's assume that we substituted A and 1. It doesn't matter what we assume, since we are multiplying 100 by 121, which is 11 squared. Now for our second substitution, we can pick any of the players, including A. It says clearly that we can replace substituted players. So we have 11 choices again. And out of the 11 substituted players, we cannot resubstitute one back in. Since one has already been substituted, we can't pull him back in the game. So any of the other 10 players are valid candidates. So we have 10 choices. And this would give us 11 times 11 times 11 times 10. Build on this for the third substitution. Let's arbitrarily say that 2 got substituted out. It doesn't matter which one of the initial players got substituted out and which one are we replacing it with, as long as it's not 1, since we are multiplying by 110, so it's already counted. So let's say there's 2 here and B here. Now, out of these original 11, out of the 11 players that are playing now, we can pick any one of them. We could pick 3 through 11, or we could pick A and B. A or B. So that still gives us 11 choices. And down here, out of the 11 players that are substituted, we can't pick 1 or we can't pick 2. We can pick any of the other 9 players. So this is 11 to the power of 4. I'll just write it out. 11 times 11. And we can't have more than 3 substitutions, so we stop here. So 11 times 11 times 11 times 11 times 10 times 9. Now, you could multiply out the whole thing, but you have to be smart on the AIME, especially in the arithmetic. So notice for 2 and 3, there's a common factor of 11 cubed times 10. And in the first, there's a factor of 1 left. I mean, in the second, so this is times 1. And on the bottom, we have 11 times 9, which is 99. This is just 11 cubed times 10 times 100. So that's 11 cubed times 10 cubed, which is 1. So you actually have to calculate 11 cubed, which would give us, let's see, 121 times 10 minus 121. That would give us 10 minus 1, which would give us 9. 11 minus 3, which would give us 8. 0, this. And we're just, so we already found this, and now we're just plopping 3 zeros at the end. So what do we do now? Now we're adding, so it doesn't even matter. These digits don't matter since we're looking at this mod 1000, which means that it only matters what the last 3 digits are, because anything before that is already divisible by 1000. So now we add 121 to this, and we add the 1, which would give us 122. Notice that we could have just crossed this whole term out once we saw the 10 cubed here, since that 10 cubed is divisible by 1000, since they're equivalent. So 11 cubed times 10 cubed would be divisible by 1000. So it's just 11 squared, which is 121, plus 1, which gives us 122 as our answer. Moving on to the next problem. Number 5. A moving particle starts at the point 4, 4 and moves until it hits one of the coordinate axes for the first time. When the particle is at the point A, B, it moves at random to one of the points A minus 1, B, which means that we subtract 1 from the x coordinate, that's 1 to the left, A, B minus 1, which is 1 down, or A minus 1, B minus 1, that's just going 1 to the left and 1 down, each with probability 1/3. And it's independently of its previous moves. The probability that it will hit the coordinate axes at 0, 0 is m over 3 to the power of n, where m and n are positive integers such that m is not divisible by 3. Find m plus n. Okay, so in this problem, I drew this quick sketch right here, where we have this point representing 0, 0 and these lines representing the axes. Now we want it to hit 0, 0 before it hits anything else. Well, we could do something like this, and it hits here. But notice what just happened. We hit the axes at this point before we did anything else. So anything coming along this line right here wouldn't work. Similarly, anything coming along this line won't work. The only other way to get to the coordinate, to get to the origin, is through this point. So our sketch, our drawing needs to come here. One of the points the particle needs to come to is here, which is 1, 1. And now this problem looks much simpler. We're just counting the number of ways from us to get to this point to this point. From that point to that point. And remember, it's probability, so it's not just important to count, but the probability of that actually happening. Well, we have 3 possible moves. We can go 1 squared to the left, that's the first type of move. 1 squared down, that's the second type of move. Or 1 squared to the left and 1 squared down, which is a diagonal move. We'll call that C for the crazy move. And our 3 options are L, D, and C. Well, notice that we could have 0 C's, 1 C, for example, something like this, and then just going here. 2 C's, and then going here. Or 3 C's. That's the only possible number of C's that we can have. We can't have more than 3 C's, and a negative number of C's doesn't even make sense. So we can just easily do casework on that. If we have 0 C's, then we're basically asked, we have 3 lefts that are needed, so 3 lefts and 3 D's. And we're asked how many ways can we arrange these? Because any possible arrangement of these 3 lefts and 3 downs would result in a valid way to get there. This is the same as rearranging L, 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 D, D, D. Now this is a very famous and common type of problem, and we're just choosing out of these 6 spots, 3 of them to be L's or 3 of them to be D. Same thing. And that's just 6, choose 3. Now if this is confusing you, make sure you watch our video on combinations and permutations before we continue. We're going to assume that you know how to evaluate these, so that would be 6 times 5 times 4 times 3 times 2 times 1. 3 and the 2 cancel out with the 6, and we're left with 20. So our answer is 20. And we need 1, 2, 3, 4, 5, 6 moves. The probability of each of these moves is happening is 1/3. So that would be 3 to the power of 6 as our denominator. What if C equals 1? If C equals 1, then once, let's say we pick this squared to be our first C, then we're basically asked to go left twice and down twice, which makes sense since 1 C should remove 1 L and 1 D. So we have to arrange 2 L's, 2 D's, and 1 C. The number of ways that we can do that, you might recognize this as a Mississippi problem from Math Count, and you can look at our video on factorials to see how to solve this type of problem. But the number of ways to do this would be 5 factorial, that's how many ways you can arrange them, but you can flip the D's or you can flip the L's, so you divide by 2 factorial twice. I'm quickly rushing through this because we do go over these in past videos and you can watch them to understand this. But we have 5 factorial over 2 factorial times 2 factorial, which is 5 times 4 times 3 times 2 times 1 over 2 times 2. 2 times 2 cancels out with the 4, and we're left with the 5 times 3, 15 times 2 equals 30 on the top. Now, the probability of each of these moves happening is 1/3. So we have 30 over 3 to the power of 5. We don't need to cancel out the 3 from the top and the bottom because maybe in the end we won't even have to do that. What if we have 2 C's? Then let's erase all of this. So if we have 2 C's, it'll remove 2 L's and 2 D's from our original 3L 3D expression. So we would have C, C, L, D. Those are the letters that we need to arrange, and that's 4 factorial divided by 2 factorial, which gives us 4 times 3 times 2 divided by 2. The 2's cancel, which gives us 12. And this makes sense. Out of these 4 spots, we have to pick 4. Out of the 4, we have to pick 1 spot to be the L and 3 to be, out of the other 3, we have to pick 1 to be the D. So that would be 4 times 3. The other spots are just C. So we have 12 over, since there's 4 moves here, the probability of each move happening is 1/3. It's 3 to the power 4. Or we could have C, and we could have 3 C's. And the number of ways, so that would be complete, and we don't need any L's or D's. So the number of ways of that happening is just 1, this long diagonal right here. And the probability of that happening, the probability of us picking C every time is 1/3 to the power of 3. So that would be 1 over 27. Or let's write it as a power of 3. 1 over 3. And that's it. These are all the cases. So we can add them up and we'll get, so let's take a common base first. We'll do a common denominator of 3 to the power of 6. So we'll get 20 over 3 to the power of 6 plus 30 over 3 to the power of 5. So our original guess was correct. We do not cancel out the 3. It doesn't help us. So we get 30 times 3, which is 150 over 3 to the power of 6 plus 12 times 9, which would give us 108 over 3 to the 6 plus 27 over 3 to the 6. Now you could add these up. We would get 150 plus 108. This gives us 258 plus 20 So 20 plus 27 is 47. So plus 47. 5 here, 1 here, and we're getting 305. What now? So we're getting 305 right there. How do we continue with this problem? Oh, right here. So this 150, 30 times 3 should give us 90. And this should give us 90 here. Because we're doing 30 times 3, not 30 times 5. And that would mean that we subtract 60 here to get 245. So we would get 245 for 3 to the 6. And that would be 3 to the power of 6, which is 6 plus 245, like the problem format states. And you would get an answer of 251. And you would put that down and you would be incorrect. Remember, once we reach here, the probability of us taking this move right here is 1/3. So we have to multiply by 1/3. That would give us 245 over 3 to the power of 7. You still should check if the numerator is a power, if it has any factor of 3, even though it most likely doesn't because of the way that we added up the fractions. Using our divisibility rule for 3, we see 6 plus 5 gives us 11, and 11 is not divisible by 3, so 245 is not divisible by 3. Thus, our final answer is 245 plus 7. That gives us 252. That's it. We just looked at problems 1 to 5 from the 2019 AIME number 1. You'll find a link to all the problems after number 5 in the description below. Thank you for watching this video. If you enjoyed or appreciated the effort that went into making this video, please don't forget to subscribe to our channel. If you want more free resources, including free courses, go to ThePuzzlr.com. Thank you.